last class? Are you there? People?
Yes, sir.
Okay. So if there are no questions from last class, let me start with where I left off last time. So if I remember correctly, we were doing binary search trees. And just to remind you what binary search trees are, they are data structures in which you have a node contains a value, and you have a left child and a right child, correct? And so this is just a tree. This is just a binary tree. But binary search trees are those in which the self.value, the value at the root, at the node, is greater than the value on the left subtree. So there's all the nodes which are below the left child, correct? So you can reach those nodes which you can reach after going through the left child, have value which is less than the value of current of the value at the top, and these have value which are greater than this. So L subtree and R subtree, correct? Which we'll often abbreviate as L and R, correct? So, and here I assume that the values are all comparable. They could all be integers, or they could all be strings, or could be any objects, any pair of which are comparable, correct? Now, how do you find a value? So, and so even before that, so we write this code for, so let's call this data structure T node, and we have a class T node, which is which has an init function as usual. And maybe I should not even be writing this, but let me do it all the same. Value equal to none. Self dot value is equal to val. Self dot LC. Let me just abbreviate it to LC. Is equal to self is equal to none, and self dot RC equal to none, correct? So this is just initializer, this thing. And now you can, if you were given a tree, how would you search for something in this, for a value in this? Def search, or let's call it find. Last time I called it search, let's call it find. Self.v. So how would you do it? So let me define is empty. Def is empty self. This is just return self dot value equal to none. The only empty tree has value none, correct? So if self dot is empty, then we just return false, correct? Now, if self dot value equal to v, then what do we do? Return true. And now if self dot value is greater than v, correct? Then what do? You have to go left, correct? But before that, you have to check if self dot left child equal to none is not equal to none. If it's none, then you just, okay, let me just do it that way. Equal to none, return false because there's no left subtree, and return self dot find self dot left self dot lc dot find v, correct? And symmetrically else if self dot rc equal to none, return false, and return self dot rc dot find v, correct? So this is what almost exactly what I had written last time, correct? Are you with me?
Yes, sir.
Now let us try to write insert. Okay, so how would I write insert? What does insert do? Insert just inserts the value v at the appropriate place in the tree. So I will write insert. So let's modify this code just to illustrate that it's very similar. The basic code is very similar. So if self dot is empty, then what do we do? Tell me.
Self dot value equal to
Self dot value equal to v, correct? Return, correct? Now if self dot value equal to v, then what do? You don't do anything, you just return, correct? Because the value is already there, you don't have to insert anything. Okay. Now if self value is greater than v, then what do? Then you have to go left. If self dot lc equal to none, then here I said return false. Instead, I will just do self dot lc is equal to t node v. I create a node with this value and put it in self dot lc. And if so, this was when the left subtree was empty. So I put the value v instead. Otherwise, I use a recursive insert and just do dot insert v, correct? And similarly on the other side, I will no, so I should no, so I made a mistake. There's a mistake I made. I should do this. And I have to return at this point. Correct? Otherwise, it will come and execute the self.lc.insert, which is something we do not want. Correct? Correct? So, and similarly, symmetrically, we can do it here. So, what do we do? Self.rc is equal to t node v, return And here I instead do this. And I change the find to insert. Correct? Very good. So now tell me, is this okay? Anybody? Do you have questions?
Yes, I have a question.
Tell me.
Suppose our tree is 4 at the root, and then on the left we have.
Give me 1 second. Give me one
Yes,
second.
yes.
So 4 at the root.
On the left, okay. Left we have, let's say 2, and then no, sir. Okay, my question is, I'm not sure this is the right tree to ask, but my question is, I think there can be situations where we have to do some rewiring, but this does not seem to.
In insert, there you don't need to do rewiring. In delete, you will need to do rewiring.
Okay, I think I need to think about it more, sir. Sorry, thank you.
So, no, it's a good question. Just think of insert as being as some form of append. You're always inserting at the end of a sequence of pointers, correct? Do you agree?
I'm not fully convinced on that.
So you follow pointers till you come to a point where, so let me try to convince you. So if you follow pointers from the root downwards, you search for essentially the value you want to insert. If you find the value, you are done. You will return in this case, correct? If you do not find the value, then you would reach a point at which this value would have been. At that point, you do this or this, correct?
So we can't have missing values, is it? Like
so non-consecutive values, you mean?
Yes, or something like that.
You can have. For example, you can even have something like 2.5 here. Now 2.75 will go here. 2.25, 2.25 will go here.
Yeah.
So this is just appending at the end of a list. So it doesn't require rewrite.
Right, yeah. Got it now, sir. Yeah.
Correct?
Yeah, thank you. Yeah.
Okay. But in delete, you are correct. We need to do rewiring. Correct?
But if we insert in this way, then we can end up with very skewed trees, no?
That's true. That's true. So we will address this question as we go along. You're absolutely correct. If we do, so what is a bad thing? If your sequence is already sorted, for example, suppose you want to insert 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, correct? How would you do it? You would first create 1, and then you would insert 2, correct? And then you would insert 3, and then you would insert 4. So you get a very skewed tree. Do you agree?
Yes.
So what is the way to overcome? We will see later in today's lecture or next lecture, most probably in today's lecture, correct? So, but let's talk about, of course, we'll see it in today's lecture. So let's talk about delete. So what is the problem with delete? I will not write the code for delete. I will instead point you to the delete for lists and show you how it is different, correct? So tell me. So let me take an example. You have 2, and this is 1. This is 2.5, and this is, let's say, 5. Correct? And these two are pointing to null. None. Correct? And these two are pointing to none. Now, if you want to delete 5, how will you do it? Tell me.
So to delete 5, I guess we could just set 4's left pointer to none. Right pointer
Right
to null.
one, right pointer to null. So you would just delete this. You would remove the pointer for 5. Correct? Let me take another example. Let me extend this example. Let me say, let's say this. Okay. Let's just say, no, what am I saying? Okay. Let me say, this one is, let's say, so what will fit here? 2.25. Correct? Correct? So similarly, if you want to, so deleting this is easy. 5 is easy. Deleting 1 is also easy. Do you agree? I mean, deleting a leaf is very easy. Just delete the leaf. Go to its parent pointer. So you walk down the tree searching for the element, looking one step in advance, meaning at the root you will look for its child, like we did for in the deletion in lists. And then when you see, so it is like, so 5 is like the last element. So you can easily delete it in a list. Do you agree?
Yes, sir.
On the other hand, if you were to delete, let's say 2.5, then what would happen? You cannot just delete 2.5 in the middle, this in the middle, because this 2.25 would also be deleted. Correct? But notice this part of the thing is, of the tree, is a list. Locally, it looks like a list. So you can promote this 2.25 up. You can attach, put this here, remove this, and put this here. And because it's on the right side of 2.25 is on the right side of this 2.5, you would still get the correct, you would still get a binary search tree, correct? Everything on the right of 2 is larger than that, and you're deleting the right child of 2. So you can just promote this 2.25 up, and you can do this via rewiring. So what you would do is not delete this pointer. Instead, you would, so let me do it in another color. You would instead make this 2.25 and you would delete this. So this is rewiring. Are you with me?
Yes.
Okay. So, okay. And now what would you do? What would you have to do if you were to delete 2? 2 has 2 children. So how would you accommodate the 2 children of 2? Tell me.
We can move 2.5 up, maintain its connection to 2.25. Sorry, we'll put that on the right of 2.5. No,
So let's,
doesn't work. Sorry.
Sir, we find the leftmost leaf of the right subtree.
or the rightmost tree of the left subtree. Yeah, exactly. So the point is, you have this, this is your node, which you want to delete. And you have a left subtree and a right subtree. And both are populated, both are non-empty, correct? Now, which elements are smaller than this? All these are exactly the elements smaller than this, correct? So, also notice that amongst these elements, the largest one is the rightmost, correct? Is the, you consider the maximum element in the left subtree, correct? That so what you can do is you can copy this here. In order to delete this element, you can copy the rightmost, the maximum. So you can copy the maximum element in the left subtree to the root, and then you delete this rightmost, correct? Now, one property of the rightmost element is that it is either a leaf or something at least which does not have a right child. So the rightmost element, the maximum element in a tree, cannot have a right child. Do you see why? The maximum element in a subtree cannot have a right child. Do you see why?
Sir, otherwise it wouldn't be.
It wouldn't be the maximum element in that subtree. The subtree contains a right child also, and the right child would then be the element you would be talking about, correct? So, so the problem reduces to deleting the rightmost element in a subtree, correct? Now, how would you delete a rightmost element? So the picture looks like you have this node, and it has either a left element and nothing on the right, or is a leaf. And these two cases we have handled earlier, correct? Whichever way it is. Let me now draw the direction. Oh no, it's the rightmost. So it is this, correct? So do you see my point? So we first write method that deletes the maximum element in a subtree, correct? And then you write def delete in terms of this. So you write def delete max and def find max. Self comma v. Self, sorry. Why you don't need v for that. So now what does the procedure for delete look like? I will let you write this delete max. It contains of dealing with these two cases. So delete self, I will not even do this complete thing, but I will leave out the base cases. So when you reach the, so when you reach the point at which you want to delete, so you basically you reach the parent of V. Correct? So you are one level above that. Oh no, sorry. You're doing replumbing, sorry. So you reach V, reach the node containing V, okay? And now you do self dot value is equal to self dot find max, correct? And self dot delete max. Do you see my point? So maybe this is also not correct. You can so if self dot no, you get the idea. Now, I will not write code. I will just point you to it. Do people understand what I'm doing? So this finds the max element in the current subtree. This is not find, it deletes. So this is finds the maximum element in the current subtree, and this deletes the max element in the current subtree. And you can compress this into one thing, delete max, and so you don't even need to do find max. You okay, let's do it this way, correct? So self dot find max, if self dot so do people understand what I'm doing? I'm getting no feedback, so I cannot.
Sir, can you discuss like,
Can I discuss which one? Sorry.
how to write delete max?
How to write delete max? That's simple. So, let me write it here. So the point is, okay, let me at least write the outline. So if self dot RC equal to none, then what do we do? Then we self so then you just
the current pointer is maximum.
huh?
The current pointer in that case is maximum.
Is maximum, yes.
Yeah, just
so yeah. So the list looks like this. The tree looks like this. This one is none, and the maximum value is here. So in this case, I would just take so the problem is I have not dealt with the base cases. That is causing the problem. So what I would like to do is to what I would like to do is to set to remove this, but I don't have this thing of the parent pointer. So then let me rewrite it. Let me assume that I never reach this point. This is unreachable. So this I have checked globally, and instead I will just do if self. So I don't even need to check that. Okay, let me check that. If self.rc dot if self.rc.rc is equal to none, so then self dot so this means that I am pointing to this, and it's I'm pointing to this, and its right pointer is also none. Correct? This also points to none. Correct? So I have then this is the this thing. So I put self.rc is equal to self.rc.lc. I take the left pointer of this and make this point this. Correct? So I splice out this one. Correct? And what are the other cases? Else?
Sir?
Huh?
So in the diagram, when you say that the pointer moves to the left child, do you mean like the pointer itself moves, or like the value shifts up?
The value stored in this self.rc is now the value of self.rc.lc. This subtree's value, it might be null, is stored here.
So that shifts up to the right. Is that
So the left child, so you are making the grandchild of this, the right child of this, and all the grandchildren on the right are larger than this. So this is a valid subtree. There is nothing on the right of this. Do you agree?
Yeah.
So I just tell me.
So, like only the value shift, right? Like the pointers aren't doing anything. That's my doubt.
So the pointer, what do I mean by pointer? I mean the value which. So each of these is an object. Here, this object is stored. In this name, the value stored is this object. It points to this object. Remember, we had the name thing on the left and the right, the value thing on the right. Those were the diagrams we were drawing. Huh? V stores one, or V stored some object. So in this case, this stores, this thing is on the, so schematically, this value, this name, self.rc, contains some value. That value is changed.
Okay, sir.
Okay. And in the else case, what do we do? Self.rc dot delete max. So you're looking one step ahead and you're doing this. Correct?
Yes, sir.
And in the delete, now you will check for one step ahead. You will start out with delete max, so it's one step ahead. And and this takes care of both the leaf and the non-leaf case, because in the leaf case, this will be none, and in the non-leaf case, it will be some subtree. Correct? Am I making sense? Okay, let me write delete also. If you want, I can write delete also. So let's write delete from scratch. So how would we write it? Or wait. Let me save this part. and
Sir, delete max deletes the maximum and then on the current subtree, right?
the delete max deletes the yes.
So shouldn't we check whether the right subtree is none and
the right subtree is
none?
no, it's looking one step ahead. Otherwise, I cannot store the parent pointer. I might have to carry the parent pointer along. So that's equivalent to looking one step ahead. So it'll be fixed in the delete. So let's do it. If so, how would we delete it? Tell me. Sorry. So how would we delete? If self dot is empty, then you don't have to do anything. Correct? If self, so if self dot value is equal to so now meaning let's write an so the problem is okay, let me take the easy way out. Let me write okay, so how would we do it? So if self dot value equal to v, then I would just set and hold on for some this thing. I know that this is the topmost value. So if I know that, then self dot value equal to none. No, I don't know this. Sorry. So what will I do? Now I do some rewiring. So basically I'm saying this can only, if self is v, this can only occur at the root. And otherwise I will define a function delete augs. So let me write that def delete augs. An auxiliary function self comma v. Correct? Which assumes that
can't we check that self dot value dot rc equal to v, and then the rc of that goes to the lc thing here points to, and lc goes to that current value instead of rc value. rc of rc goes to that.
Okay.
Oh no, that might also have
no, that's true. So let me do it that way. So if self dot value equal to v, you do
I was saying self dot value dot rc. I think that work.
So let me even do. Okay, fine. So self dot value equal to one second. Just give me 1 second. Self dot. So when I did this self dot rc, and now I have to return. So okay, fine. So self dot value equal to v. Then self dot lc dot so now I check. So basically, I'm at this point. I want to delete the maximum value here. I want to copy the maximum value here and delete this value. Correct? This is an LC. So let me check if self.lc .rc. So, and I want to preserve this thing that self.rc is not none. Correct? So I want to carry one step in advance. So if self.rc is equal to none, self.rc equal to none, then what do I do? Then self dot one second, what do I do? Then this is the maximum value. So LC's value is the maximum value, and I just say self dot LC is equal to self dot LC dot LC. So I am at. Do you see my point? So I am at this value. V is here. I have the left child. The left child has this is the left child. The right child of this is empty. I'm in this case, and the left child is whatever it is. So the maximum value is this, and now I just copy it instead of V. Correct?
Yes.
And else, what do I do?
Sir, we should change the value of self dot value, right?
Yeah, sorry. Self dot LC is equal and self dot value is equal to. So I should do this before. Self dot value is equal to. No, 1 second. Is equal to self dot LC dot value, and I put this before this. So I should have written it in the other order, which I will now do this. Now is it fine?
Yes.
Okay. Else, what do I do? Else I now we know the self.lc.rc is not none. So else I say self.value is equal to self.lc.findMax and self.delete max. And this might seem wasteful because I'm traversing the left subtree twice. So in fact, and it is wasteful. So I should instead return the value in delete max itself. So I should make this, let's say, self.lc.delete max, sorry. Self.lc.delete max, and I should replace this by self.lc.delete max. And now let me go back and change here. So I spliced out rc.rc equal to none. I said rc.lc, and the value of rc was this thing, correct? So I do temp is equal to self.rc.value, correct? And return temp. And here I say return self.rc.delete max. Do you agree? Now this is just one this thing, correct?
So could you repeat what you said about delete max? I mean, you changed something in delete max.
Yes. So what I changed is, so first I was saying that we go to the maximum value and delete it. But I know the maximum, so this involves traversing the tree. correct? And I can simultaneously return the value that I have deleted.
Okay. Yeah.
So instead of first traversing the tree to find that value, storing it somewhere, and then deleting that value, then going down the tree again and deleting that value, I do it in one shot.
Okay.
So, correct? So I do it in one shot and return that value, and I set self.value is equal to self.delete max. So that value is returned and it is stored in self. Correct? And now what do we do? It's not complete yet. Nah? Now, else if self.value is less than v, self.value is greater than v, then what do we do? Then you just do self.lc.delete v. So if self.lc, then self.delete v. Otherwise, you else if sorry, you don't even need to do else if self.rc delete v. So tell me, does this make sense? And you can return at the end. Doesn't matter. So tell me, any questions, comments, corrections?
It is self.lc.delete max, right? What you're
No. Where? This is it.
Yeah.
In the previous.
Yeah, it's not clear.
Sorry.
Okay, sir.
Now is it okay?
Yes, sir.
So this part is clear, correct? And I've already gone way over time related to what I wanted to cover. But let's see. So now we will talk about, like you say, we can create unbalanced trees as a result of these operations. We saw an example here. And even if your initial tree is unbalanced merely by deletions, you can make the tree unbalanced. Insertions and deletions together can make the tree arbitrarily unbalanced, correct? So now the question is, and we saw last time that the running time is proportional of each of these operations is proportional to the depth of the tree, correct? So now, how do we maintain that this depth is small? So first, let us see what is the so how do we try to maintain this? So the ideal thing would be to have a perfect binary tree. You have height h. So so this is h is equal to, let's see. So this is 1 second. H equal to 0, correct? H equal to 0. So no, this is not h equal to 0. This is h equal to 0 is an empty tree. So there is no node. So the size of the tree is 0. One node tree, size is equal to 1. H equal to 2 is a 3-node tree, size 3. Okay, and so on and so forth. So now you can see that so for a height h tree, the size is 2 to the h minus 1, and it's an easy inductive exercise to prove this. Prove this by induction, correct? Structural induction on the tree. Do you agree?
Yes, sir.
So what does this tell us? This tells us that h is equal to log base 2 of size plus 1 for a perfect tree. For a perfect binary tree in which this height is h. There are h layers. Correct? Now, but your n might not be divisible by so your size plus 1 might not be a power of 2. Size might not be a power of 2 minus 1. Moreover, maintaining this tree, even if it's a power of 1, will be very hard. Power of 2, it might be very hard. Correct? So we have to deal with slightly imbalanced trees. And this, so the first idea that comes to mind is that for every, you say that the size of LC, which is minus size of RC, is less than equal to 1. Correct? So you try to maintain as balanced as possible. So for example, you do this, this is of course balanced, LC and RC are both 0. Then you do this or this, these are also balanced. And then you of course have the perfect tree. And so you alternately add, you alternately add to the left and right, something like this, correct? So you add to the left, and in the next this thing you add to the you add to the right, something like this, correct? Do you see my point? But the maintaining such a tree is again very complicated. Maintaining a binary search tree in this format is very complicated, correct? So the size balance thing is very hard to maintain. So instead we maintain a weaker invariant, which is that the height of LC minus height of RC is bounded by 1. Correct? So this is called height balanced trees. Height balanced. This was size balanced. And so we will show that every height balanced tree is also of logarithmic height in the number of nodes. So how do we show that? Well, so you want to show that the height is less than some log of size something, correct? Roughly is something like this, correct? Log to base some base or whatever, correct? So which means that the size is greater than equal to some c to the h for some constant c. So let's say this is to be c. This is what you want to maintain, correct? That every tree of height h has size exponential in the height. And which trees am I talking about? of every height balanced. Size at least exponential in the height. Correct? In particular, if we can show the smallest size tree of height h is greater than c to the h, there exists a constant c such that the smallest size tree of height h is greater than c to the h, then we are done. Are you with me?
Yes, sir.
So, how would you form the smallest height balance tree? So, what is the smallest height balance tree of height 1? So, let's draw height versus size of smallest, or let us say smallest sized height balanced tree. Correct? So if height is 1, you just have one tree. So there's nothing to talk about. For 2, you have, what is the smallest height balanced tree? Tell me. If you remove, I claim this is the tree. No, am I making a mistake? No, I'm not making a mistake.
So either way is okay, right? Either way is okay, right? The left subtree or right subtree.
If I delete any edge in this, is any subtree of this a height 2 height balance tree? If I delete this vertex, if I delete any vertex, sorry, if I any subtree, so any vertex I delete, then the height will go down. So I cannot delete this vertex. Now let's do it for 3. So you have 3 levels, and at least this path is present. Now, this height is 3, so this height must be at least 1, at least 2, correct? So the levels are 1, 2, 3, correct? So this must be 1, and now is this height balanced?
So no, right?
Why not?
So if you delete the right subtree, it will
So
be.
you are saying, so why is this not height balanced?
If you delete the right subtree, it won't be height balanced.
If I delete the right subtree, it won't be height balanced? No, what is the height of this? What is the, so these two differ. No, this is height balanced. This is height balanced, correct? Let's go to 4. So in 4, what is the thing? You must first draw a 4 length thing at least. Now this one must be at least this thing, and this one must be at least this thing, correct? So basically what I want to say is that the left sub, so let's call this T1, this is a node with T1 on the left. And what is T0? T0 is just empty, correct? And T0 on the right. T0 on the right. Meaning, no, this is not the way to draw it. Yeah, so this is the empty list. Fine. So this is T1. Here you have a node and you have T1 on the left, T2 on the left. So this was T2, correct? This is T2 and T1 on the right. So this is T1. In general, so this is with T3 on the left and T2 on the right. So I claim that at height h, you have, meaning TH1, TH plus 1, or TH looks like is equal to a vertex with TH minus 1 on one side and TH minus 2 on the other side. Let's prove this claim. So how would you prove this claim? What do we want to prove? That the height difference in these two trees is 1 at most, TH1 and TH minus 2, and recursively for every subtree inside them. So by induction, inside them, the height difference is 1 only, correct? Between every pair of children. And here the height is, this height is h minus 1. So the height from here is h, and here it is h minus 1. Correct? Am I making sense? And now we want to prove that any subtree of this does not satisfy this property. So if you reduce the, if you remove any node from TH minus 2, you will not get a tree of height. Then the height will decrease beyond h minus 1 by assumption, correct? Or it will not be height balanced. Similarly, if you remove a node from here, it will the height will go down, or it will not remain height balanced. Do you see my point? Hi, are people there?
Yes.
Yes, sir. Yes, sir.
So, are you following me?
Yes, sir.
So, basically, I'm saying that there is a TH must look like TH minus 1, TH minus 2, and a node. So, the size of TH is precisely equal to, where this is the minimum tree of height h, is size of TH minus 1 plus size of TH minus 2 plus 1. Correct? So, so this recursion is majorized by the Fibonacci recursion. Correct? Let's call this T. TH is TH minus 1 plus TH minus 2. Correct? So it is less than equal to. So this implies that, because I'm dropping the 1 here, correct? So it is majorized by the Fibonacci recursion, and the base cases also match. You can check, and you know that TH is therefore less than the Fibonacci, which is something like c to the h for some c, some like root 5 plus 1 by 2 to the Something like this, correct? So you can derive that. Is less than is less than c to the power h for some c, the golden ratio probably, correct? Are you with me?
Yes, sir.
So therefore we have proved that this is what we had set out to prove, and therefore the height is logarithmic. Is the argument clear?
Sir, shouldn't it be greater than, because there's a +1 there?
Which one?
Shouldn't TH be greater than equal to TH minus 1?
Sorry. You are correct. You're absolutely correct. So TH is greater than equal to this. So yeah, we wanted a lower bound on TH. That's correct. So H is less than log of FH, which is equal to, is less than log of C to the H. FH is less than C to the H, so this is less than H log C for some C, correct? No, what am I saying? I'm watching time, sorry. So what am I saying is that this is equal to the size of H. Size of the tree, correct? So size of H is of every tree of height H is greater than C to the H. So H is less than log of the size of H to base C. That's all I'm saying. Do you agree? And this you can think of as n in the case. So if there are n values stored, then the height is less than log n. That's what we wanted to prove. Constant times log n, correct? Are you with me? Thanks for whoever pointed it out that the inequality was in the wrong direction.
Yes,
Sorry,
sir.
could you repeat the big picture of what we were trying to do again?
Okay, so the big picture is you want to prove that if the tree is height balanced, then its height is less than logarithmic in the size of the tree. Every height balanced tree is of small height, of logarithmic height, correct?
Okay, sir. Yes.
And to do that, we show that the smallest tree of height h is large, has lots of nodes.
Okay, sir. Okay.
Correct?
Got it, sir. Yeah.
So we can therefore this follows, correct? And this is so TH is majorizes the Fibonacci series, and therefore we have this bound. Correct? Okay, so let me stop at this point and go to so next time what we are going to see is how to make the tree height balanced. How to make the tree height balanced at all the times. So let me try to introduce it. So suppose you have a tree that is height balanced. At any point of time, you have a tree that is height balanced, correct? Now you add a node. So you insert the node via this procedure. Which procedure? This procedure, correct? This procedure. So what is going to happen to the height balance? Tell me. How badly is it going to get affected? Will it remain
most by 1?
At most by 1. And at one point, correct?
Yes, sir.
So one node would get I'm lying there. So you will get one path which is longer than the other paths, at least two longer than the other paths. Correct? So height balance means that every root to leaf path in the left subtree, not every. So I mean, it is so one path might get very long. Correct? That's what I'm saying. Correct? Now you will somehow preserving this property, preserving the search property, change the tree locally so that the height invariant is restored at that vertex. You would hope that this restores it for the entire tree, but that might not be the case. You would have done some restructuring of the tree, so some other path would have gotten longer, and then, but it is at a lesser height. This point at which the difference in heights is more than 1 or is exactly 2 is gets smaller and smaller and smaller. So in height many steps, you can restore the balance. That's what we are going to show next time. Okay? Is the broad idea clear?
Yes, sir.
So to re-emphasize, suppose you have a tree. This is a tree, left subtree and the right subtree, correct? Left subtree, suppose, has the deepest node in the left subtree has height h plus 1, h plus 2, sorry. And the right subtree has deepest node, which is height h, correct? Then then there is a problem. This tree is no longer height balanced, because at this node, the left part is way too bigger, at least too bigger than the right, correct? So we have to restore that. So how do we aim to restore that? By decreasing the height of the left part and increasing the height of the right part. So that is like a rotation around this pivot. And we will make this more precise next time. Are you with me?
Yes, sir.
Okay. So any other questions?
Excuse me, sir.
Tell me.
I had a doubt from previous class. Can I ask?
Yeah, sure.
Yes, sir. In the previous class, we described a method to without replumbing by creating another class. I have a doubt in that.
Should I open the? Tell me.
Yes,
Before
sir.
where?
Defining the class of the linked lists, my list. Yes, sir. Yes, sir. Yeah. This. Yes. So in this, suppose I did the following thing, but my code was getting a recursion error. Uh, uh, I did like uh, 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 can I send in the chat?
Maybe we can fix a time and can ask
Yes, sir.
outside.
I did the following thing, but this was getting recursion error. Can you explain why?
You have sent it on the chat.
Yes, sir.
What is this? I just on this piece of code, this is just so I'll have to look at the code in this thing and
Okay, sir. I'll mail you.
Mail it to me, and then we can talk about it at some point. Correct?
Okay, sir. Thank you, sir.
Thank you.
Sir, can you repeat the definition of height balance tree once again, sir?
Height balance tree is you know what the height of a tree is. Height of the tree is the length of the longest root to leaf path. Correct? So a height balance tree is amongst all the paths that go leftwards and all the paths go rightwards, the difference in the so basically the heights of the left subtree and the right subtree differ by at most 1. So the deepest path on the left side and the deepest path on the right side differ by at most 1 in length.
Of the main tree, right?
Of any node in the tree.
Okay, so of any node. Okay.
Correct? So, 1 second. Yeah. So, like in these subtrees that I've drawn, correct? Look at any node. This has a left subtree which is height 1, height 2, and right subtree which is of height 1. Sorry, what am I saying? So this is height, just alone it is height. So just alone it is height 1, this one is height 0, correct? There's no subtree there at all. Here you have height 2 and this is height 1. This is, and similarly for this node, it is height 1 and height 0. So is it clear?
Yes, it's clear.
Similarly here and here, there's height 2, height 3 and height 2 and so on, correct? Okay. More questions? Okay. So we meet next Tuesday and there will be a quiz sometime next week. So please attend classes, correct? Okay, thanks. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.